Welcome everybody. Thanks for joining the Hot Plate Welding Tales of Triumph webinar. My name is Jason Dornboss. I am a sales manager at Extol, and I have been here for over 15 years, and I get excited about hot plate welding. Mitch.
Yeah, my name is Mitch Ryan. I'm a sales engineer here. My role here at Extol, I do two things. I help customers find what the optimal technology is for their specific applications, and then I help tailor that equipment to their automation needs and their assembly needs. I put this slide up here, give you some context who Extol is. We've been solving plastic manufacturing challenges for 40 plus years. I'm sure some of you are familiar with these logos. In the chat, which of these logos don't you like? No, I'm just kidding. Don't do
throw
that.
down.
No, don't do that. Another slide here, just who Extol is. You can kind of think of us in three distinct areas. We've got our engineering services on the front end. So again, that's kind of where I work a lot, helping customers with their design development, whether prototypes, validation on the front end. Then we have our assembly technologies. You can see there's 8, and we'll even do some ultrasonic. There's other assembly technologies that we do outside of these, but these tend to be the core that we represent. And we're focusing specifically on hot plate welding. And the third portion of that is the equipment. How we actually deliver all of these solutions, whether it's an integration package, whether it's a standard machine, or whether it's custom automation.
We want this webinar to be interactive and engaging. So if you've joined our webinars in the past, you know that we use the meeting chat to have a big dialogue going. So if you've got questions in your head and you're curious about something, please put that into the chat. We'll do our best to address those as we go along. Mm-hmm. We might tell you that it's something that we're going to hit on later, knowing that we've got a lot to talk about, and we'll try to address every question that comes in, and we want it to be, a good dialogue.
Yep, exactly. And if we don't have time to address them on the call, we will follow up offline. We have the messages and receipts, so we can follow up afterward. You want to run through the agenda for today, Jason?
Yes. So we're going to talk about how hot plate welding works, just give you a basic overview so you have a general understanding of what the technology does. And then we'll look at some common problems with plastic welding. And then we'll talk about, we'll tie that in with some tales of triumph. These are real project stories where we've seen the issue and the problem, and then we've found a solution that works really well for that particular application. And then lessons learned. What do we learn about hot plate welding and plastic welding, and how to tackle a hot plate welding project? So the first question that we have is, why did you sign up for this webinar? And put this in the chat, are you hoping to learn more about hot plate welding just in general? Do you have a project that you're curious about, something specific that you're hoping to learn? Please drop that in there. Some people I know are here for the free lunch. We learned that earlier, so you can drop that in there. So we're looking for at least a bunch of responses saying, why did you sign up for this webinar? Mm-hmm. And we're going to sit here and wait until we get some
general knowledge.
Thank you, Randy.
You're in the right place.
Evaluating alternatives for plastic joining. Okay. All right. Good. We definitely can talk about that.
I like the new and old technologies. That's kind of a piece we're going to touch on too, Sven, because hot plate welding has been around for years. I mean,
a long time, decades.
Has it been hundreds? I don't know. It's been a long time.
Decades at least.
Yeah. That's hundreds, probably exaggeration. But how hot plate welding is implemented, and even how we do hot plate welding, is different from other companies. And there's a couple areas that we do that make the welding process more advantageous, and maybe give a different perspective on hot plate welding as well.
Tom's looking to weld or tack some EVA foam, 2028 program for a floor console. That's a great application for hot plate. Understand process and comparisons to laser. Interesting. Okay. Bought a machine, bought tooling, wanted to know what problems to expect. Ooh, good one. Lots of ultrasonic welding. Hot plate welding is more popular. Great.
Well, if it's Extol equipment, he shouldn't have any issues, right?
Straight.
None. You're set. You're good.
All right, awesome. These are all great reasons to be here. So you want me to run through this process?
Yeah, go ahead and run through the hot plate welding process and just touch on maybe how we're a little different from other suppliers.
Hot plate welding in general concept is fairly straightforward and simple. How it's executed is that's where the all of the technical expertise comes in. So first, in general, what you have is two plastic parts. They have weld ribs on them. You bring them into contact. These plastic surfaces are touching a heated tool. Heated tool basically means a piece of metal that has been machined to match the welding contours of the part. That heated tool is hot. Maybe it's 500 degrees. Maybe it's higher than that. It's programmable. So you touch these plastic parts onto the heated tool. You melt that weld surface, and then you remove the parts from the heated tool, get that heated tool out of the way, and then bring the parts back together to weld. We apply pressure. The two very key components in hot plate welding and any plastic welding technology is heat and pressure. How do we apply heat to the weld and then apply pressure to get those plastics to bond? Yeah. And with hot plate welding, we're doing it via conduction and then a pressure afterwards.
Yeah. One distinction here too. We're talking about actually coming into contact with the hot plate. So some customers that we work with, they use hot plate in a hot plate hover application. And we can do that as well, but what we're focusing on specifically with this presentation is coming into contact with parts. And we'll touch on why that's important as we move through the slides here.
Scott asked about real-time videos. We are going to show some videos. In fact, the very next slide here is a quick video just to show what the hot plate welding process looks like.
Great setup, Scott. I appreciate that.
So here you see somebody loading parts into nesting, a safety door closes, the hot tooling comes forward, parts are made, they're touching that heated tool just for a very brief amount of time, and then now they're being stuck together. The melt time in this particular application was pretty short because the heated tool was very hot, like 800 degrees Fahrenheit hot. And that allows us to quickly get that heat to soak into the plastic and then move on to the seal phase of the cycle.
Yeah, let's pause real quick on that image right there that you have on the screen. So one of the things on the top, when a lot of people think about hot plate welding, I guess what are some of your general perceptions of it?
Yeah, what do you typically think of when you think of hot plate welding? Do you think the best process in the world, or do you think something else?
Yeah, when you see this part here, what maybe stands out as surprising to you for this one? Jason's kind of highlighting with the cursor here, a bit of a leading question here. Yeah, large, bulky machines.
Okay, yeah. Primitive.
Yes.
The gutter for flash protection.
Exactly, that's
3D
right.
weld rib, yes.
That's right, Scott. That's what we're trying to highlight with this one here. You can see that we've got a built-in flash trap on this part here, and you can produce, this is a handheld part that you're using, so the flash protrusion would not work for this. So because of how we're controlling temperature, heat, the speed at which we're running this, we're able to make very clean and precise welds.
Yep. So we're protecting flash from getting out. It's got a very clean aesthetic. It's got a contour. Hot plate welding can handle contoured parts.
Yep. Yeah, we're heating both sides of the part.
Yes, both sides of the part get heated. In the video, it only focuses on the top, but the same thing is happening on the bottom.
Exactly. Yeah.
There's, as I mentioned before, there's two main things with hot plate welding and any welding technology: heat and pressure. So on the heat side, we're controlling the temperature of the heated tooling. We're controlling how deep into the plastic part that is being displaced. So the plastic comes into contact with the heated tooling, and then we push a little bit more, sometimes say 10 20 thousandths of an inch into that tooling, and we're displacing some of that. So that's the depth that we're melting. And then how long do we sit there? That's the time component. How long do we dwell in that position to allow that heat to continue to soak into the weld joint? That's all controlling the heat portion of the cycle. And then when we get to the pressure side, then we, again, our depth is how much compression are we applying to those parts? How much displacement of material are we getting? The forces that we're applying during that pressure phase. How hard do we press? And then how long do we hold that? Those are all factors in the pressure side of the hot plate welding process.
Yeah.
I've seen some questions come in.
Yeah. I'll just, before we get to the question real quick, the resolution and control on these two parameters are critical. So having constant heat around your surface is absolutely critical. Even getting to the right set temperature, like maybe it needs to be 800 F plus to weld those parts. And then pressure, the same thing, making sure that you have the really great control on the pressure that you have, the depth that you're welding to, all that's critical. There was one question that do you work with engineers on how to design these flash trap features? Luke, you made a great point. We do have our design guidelines on our website. I'd also say we have a team of dedicated applications engineers to help customers design their parts for their specific application. So a lot of times flash traps have a bunch of different, they look different. You know, like that flash trap wasn't actually covering the flash itself. It was just more of a step. There's several ways to approach that, and each design has its own pros and cons for those flash trap designs.
Max asked a question about, do you control the weld depth by pressure or depth? And the answer is both. We actually can program the welder to either go by pressure and monitor depth, or go by depth and control the amount of pressure available to hit the depth. So both, depending on the application. The other question that I saw in here was about surface area. So you're foreshadowing a little bit.
Yeah, I'd say let's hold off on that question because we've got a couple answers for that one that we'll round it out. There's a lot more that goes into the surface area question that we'll try to lay out throughout the presentation.
Yep. All right.
Let's see. Can hot plate welding be utilized to assemblies that contain electronics?
Yes. Absolutely. 100%.
You'll have to keep some spacing and make sure that there's insulation to avoid damage to the electronics, but it's very viable. And then, does the form tool require a particular temperature or just the plate tooling? I think you're referring to maybe the nesting, that like the upper and lower nesting that captures the parts. There's no temperature in that. And then if it's the contour plate that we had, there wasn't that much of a contour on the tool that you saw in the video that would require any heaters in that actual tool set. But we have certain applications where you've got a contour in a part where, say, the weld profile steps down a few inches, maybe a few inches. In that instance, you would require secondary heaters to make sure that you had
even temperature at the surface.
Yeah, exactly. All right. So these are some common issues with plastic welding. You've got tricky materials that we're working with. That we put tricky materials. There's no really good way to say it succinctly. Like materials that have a sharp glass transition. So when you bring them to the melt stage and you take them off the heated tool, they'll quickly skin over, or they'll quickly cool to a point where they're no longer molten. That's a very common issue with plastic welding. Getting inconsistent strength in parts, inconsistent stack ups to parts. We all know plastic parts are molded or warped, and even warped parts is another one that you're dealing with here. Sticky and stringy parts, and then messy maintenance on a hot tool. I'm going to keep rolling here, I think, through the controlling work. Do you want to stop me if there's any questions if they come in that we should
we're getting
address?
Some questions, but I think we're going to address some of them as we move forward. So let's keep moving.
So we're going to go through these next few slides to kind of address these, not in this particular order. We'll start off with work parts. So this is for larger assemblies or assemblies that have a large surface area on them. So maybe there's a lot of internal ribbing. One example is speaker boxes. Those tend to be large housings that you have large plastic parts, and polypropylene. And if anyone has worked with polypropylene, most people call it polywarpylene. So the reason hot plate welding lends itself really well to larger parts or parts with a lot of surface area is because we normalize the weld joint. So let's zoom in to the plastic part weld profile. And this kind of simulates, I guess, probably the other image of the part where you've got some high and low spots here. If you were to join this part together, bring it to a molten state and join as is, you've got a lower component on Let me get the laser here. The right side of the screen here that would absorb all of the force or a majority of the force, and you'd get minimal force on this part, which could create leak paths. So hot plate welding, you bring the hot tool in to contact with it, it flattens that weld surface. And then when you bring the two parts together, now you have two perpendicular surfaces.
Parallel, not parallel.
Whatever. Semantics.
Yes.
Two parallel surfaces, not perpendicular, that would not weld. And both of those have an even force distribution across the surface. So that's why we like to use the hot plate welding for those larger parts to take out the warp. So when we talked about surface area before, that's one of the areas that one way we address that question. Let me see what other questions as they come up.
One of the questions is, does this work for welding thin sheets to larger bulk parts? So you mentioned 50 to 200 micron. Hot plate welding really wouldn't be successful with those thin sheets because there's not enough material in the thin sheet to have any kind of a heat affected zone. We want to melt and have a little bit of a heat affected zone and have still some material behind it so that we can drive it into the next part. Usually with thin sheets like that, then we're talking more about film sealing, and there's different ways to do film sealing.
Yeah, more film seal application, I'd say, at those thicknesses. Do you monitor and control the part surface temp before getting heated? We can do hot plate welders press side or do them offline, but what's critical is consistency of the parts coming into the system, because then once you set up the process, if you're getting parts that are drastically different in temperature, then you have a set melt time that you're resting on a tool. If you are dealing with a cold part before and then you get a warm part, you're going to have a puddle of plastic. So you can do both, but consistency is more important running part to part. Does the part stick to the hot plate? How do you make sure they are released from the hot plate?
Yeah, we'll talk about that one.
Man, we must have plants in this crowd.
Right.
They're leading they're asking all the leading questions. Yeah.
You need to clean the parts before welding. Depends on how dirty they are. Usually, I don't think people are cleaning parts before unless they're covered in dirt or like mold release potentially. You do want to remove contaminants, but usually we don't see people having to clean parts before hot plate welding.
Yeah.
Warping in this view is taken care of by the melt process, but at some point, can you talk about how the tools themselves might hold the part square? Yes. So if you've got a lot of warp and it's even hard to get those parts into the nesting of the hot plate tooling, our welders have a feature called part pickup, and we can use that basically to bring the press tools together before we've melted anything. So we can use the forces available to us in the press tooling to push those parts all the way into the nest, then fire in the clamps that hold those parts into position, open the press, start the weld cycle. So now we take, if you've got a part that's like this and we push it together with the press tooling, now it's holding it flat while we do the weld. Depending on how warped the parts are, that can induce some stress into the overall part. But we've seen plenty of applications where that works really, really well, to pull a little bit of that out to get the parts into the nesting, do your weld, and then you've got a good part afterwards.
Yeah. And the best way to remove mold release for this process, I don't know if I have a great answer for that.
I don't have an answer for that, but maybe somebody else on the call does. If somebody knows the answer to that question, type it into the chat. How do you remove mold release from a plastic part? And really, it's more about just trying to get it off of the edge or remove any concentration of it from the weld rib, which
it's more minimizing impacts, because there's applications we do with mold release on the parts is pretty typical. It's a contaminant, so the less you can have on the part, the better. So the additional benefit of plating those surfaces flat is we can control the stack-up tolerance. So this is one application we have, or one of several types of applications where you've got a part encapsulated in a housing that may have areas that protrude into another portion of the assembly. So you've got stack-ups internally that you need to control on the weld process. And you've got maybe some other parts that are encapsulating the outside of that part. And then that goes into a larger assembly. All these tolerance stack up on themselves. Our platens, the position of the platens are controlled in 1,000th. You probably want to assume a little more for the stack up because you've got some part inconsistencies with plastic welding, but we can pretty reliable hit plus or minus 5 thousandths because we're planing those parts flat, even with inconsistent parts.
Yep. Scott says only the energy directors, and with hot plate welding, we refer to them as like weld ribs or sacrificial ribs.
Yeah.
But yes, those are what really need to, that's where the welding's happening. So that's what we want to remove any contaminants from.
Yeah. Yep. There was a great question from Sven about coatings that we can use, surface coatings, PTFE, chrome. I'll focus in specifically on welding HDPE, and our typical approach to that. It's actually a common hot plate welding material that we use. And we have two different approaches for that. We either use the Teflon coated tools, that's what you can see here in green along the right side. But for certain materials, either it's the customer doesn't want to deal with recoating those tools, or it's a lower volume, or there's additives in the HDPE, maybe use or something else that make it easier, that it can that the Teflon coated tools won't even work. We'll use Teflon sheets. We'll actually clamp those to the heated tooling and then use those to ensure that the HDPE does not stick to the hot tool. Without that coating, it would stick and string no matter the temperature that you use.
Teflon sheets can be nice when they're whatever you're welding to, you know, in HDPE's case, if you're wearing through coatings really, really quickly, it's a lot less expensive to just replace a Teflon sheet than it is to have tools recoated, which is very common. It's common to have Teflon coated tools recoated. It's just a matter of how frequently do you have to do that, and if that's cost prohibitive, then Teflon sheets can be a really good option. Yeah.
Most people, they hear this Teflon tooling as an option and think, I use Teflon coating for all of my applications, in which case we wouldn't recommend it. And there's a couple reasons why. The recoating is part of it. It's not a very durable coating, and it has a temperature limitation.
Yep.
So I'll go to this next slide here. We typically weld, so for hot plate, a lot of the materials we deal with, this is a polypropylene application, will weld at 800 degrees Fahrenheit plus. And that helps with a couple things. At higher temperature, you're reducing your cycle time. That's one of the benefits you have of it. The other one is if there's material that builds up on that plate, it'll burn off. So you won't have any buildup. You have to constantly maintain and scrape off the plate. This application here goes into a large automated cell, and it just consistently runs with very minimal maintenance. We have a proprietary coating that we use on the hot plate for these sort of applications that just runs over and over again. And recoating the tools, I mean, we don't even typically list it as a wear item because it's a very dense, very durable coating, I'd say. If there's glasses, like a high glass or filler content, in that instance, you may have to recoat those tools more, but we have applications where we'll run 15, 30% glass. 30% is the upper limit, though. Above that, you're going to start marring that surface.
Is the heat plate temp at continuous, or do you heat it up when necessary? It stays continuous. So because we're heating up a large chunk of steel, we get that up to temperature. It can take anywhere from 10 minutes to an hour or 2 hours if it's a really large hot plate to get up to temperature, and then we just maintain it right there. We have controllers in there that are monitoring the temperature and, you know, making sure that the surface temperature of the heated tooling stays as consistent as possible.
Yeah. We've got several thermocouples located across the profile to ensure that it's an even distribution of heat. So the other one, if you've got applications that have a high burst requirement, we're talking 500 PSI plus, or you have applications that have a lot of surface area, force is essential. Having high force. You want to speak a little bit to that, Jason?
So that was actually one of the questions earlier was, you know, what about surface area? And that's actually what matters is the surface area. So if you have a lot of surface area, you need a lot of force to be able to get the pressure into the entire weld. So what we've done with our welders is we actually have a significant amount of press force available to us. Our Titan 2000 has 2,000 pounds of press force, the smaller welder. And then we have a Titan 4000 that has 4,000 pounds of press force capacity. And then our largest welder, larger standard welder, the Rapid Conductor 2040, that has 6,000 pounds of press force available to us. That sounds like a lot of force, and it is a lot of force. But in certain applications, think about, maybe some of you are familiar with these. Semi trucks, the engines in there, they have a degas bottle as well, but they're massive. Like they could be anywhere from 50 inches wide, 40 inches wide, like big parts. And then there's all kinds of interior weld ribs. So the surface area is really large and the weld ribs are thick. And that part needs to be able to withstand a significant amount of pressure. And so it has to be a really strong weld. That's why you need a lot of force when you're welding. Otherwise, it's going to take a really long time to get to your melt depth. You're pushing your part onto this hot tool, and without enough force, it's going to take a long time to get to the melt depth that you need. And then when you're trying to weld and seal them together, you need a lot of force into that weld geometry to get it to bond.
Yeah. Imagine, I guess, for all you woodworkers out there, imagine if you just did a glue layup and you put the two parts together and you didn't put any clamping pressure on there. You could get a decent amount of force on there, but that pressure is essential to get the maximum force that you can when gluing those parts together. Think back to that earlier slide that we had where you had the fire, the heat, and then the pressure. Controlling those are essential. Increasing that pressure, that seal pressure, can increase the force. There was
how much higher than the melt temperature of the plastic do you like to be? That's a great question. I don't know that there's any set formula for, if this is the melt temperature, then you have to be at the X. Yeah. I like Tomer's, is it mainly cook and look? It's, in a way, yes. There's a wealth of experience from people like our lab engineers and others that are processing these hot plate welding applications where you go, okay, well, I know that, polypropylene likes to weld well at 500 degrees or 800 degrees. So it's a little bit of, experience, and it's a little bit of, trials to find that optimal process parameters.
Yeah. Kevin May's question, what wall stock is needed to achieve 500 PSI? Excuse me. Great question. So you can typically expect, it's all material specific too, but probably around 80%, I'd say, parent material strength of that wall thickness when you're welding with hot plate welding. Now, your pressure that you're placing on that joint is going to maximize that force. So in certain instances, if you don't get enough pressure into the weld joint, you could be around 50% parent material strength or even 30% parent material strength. In order to get up to that 80% parent material strength, you'll need to have the higher pressures. But that's typically what we look at, probably around that 80%.
What's the maximum retention force in HDPE welding? Does it depend on the material volume being welded? Are you asking about how strong of a weld you can get with HDPE? Maybe you can chime in there and we can address it.
Yeah, again, that probably be around 80% parent material. And it depends on open time too, how large the parts, a lot of different things.
I can say this too, there's a lot of applications where we, the joint is, the weld rib width is designed to be slightly, maybe 20%, maybe 50% larger than the wall thickness of the part. And by doing that, then you're able to maximize the strength of the weld so much that the weld is not what fails when you run, strength tests, whether it's a tensile test or a burst test. It's failing elsewhere because the weld becomes stronger than the wall thickness.
Yeah. It's critical too when we're talking about weld forces to think about how the hot plate welding process is actually set up. So again, this is a distinction on how Extol typically approaches. We typically approach from a servo perspective. We've done pneumatic welders in the past, but servo is where we lean. Jason, you want to speak to that? Why do we typically lean servo? What's the comparison processes?
Let me walk you through this here. So there's pneumatic welders on the left, and with a pneumatic welder, or in some cases a hydraulic welder, the way to control that process is using hard stops. Those hard stops are mechanical features that literally touch each other during the weld process to control how deep that plastic part is pushing onto the heated tool, and then again how deep the plastic parts are pushing into each other. With a servo-driven machine, servos have a lot of force capacity, and they have precise position control. So the stops aren't necessary. That's important. So when we come together for the melt phase, with a pneumatic welder, how do you know that the whole weld surface is being melted? You can tune out that, you can adjust the positions of your hard stops, but there's not really good feedback to know I've melted my entire surface. In a servo-driven welder, you can dial in the amount of melt that you're applying to the part, making sure that 100% of that weld surface is making contact. And we know we can monitor the force being applied. So if for some reason the force drops off, that is a flag. The machine can flag that and say, oh, the force, we didn't hit the amount of force we usually see to melt this part. My guess is that something is wrong with your part. Maybe there's a big short shot, or the parts are shorter for some reason, and it's not melting the entire surface because we didn't use the amount of force we needed. Then when we go to the open phase, now we're pulling off of the heated tooling and trying to get that heated tooling out of the way as quickly as possible. A pneumatic welder, you have to open it all of the way, and it moves slower, where servos are fast, and you can minimize the amount of open so that we can bring them back together quickly. This is important to what Mitch was saying earlier. There are some materials that they want to cool off and skin over really, really quickly. So by minimizing the open time, we enable hot plate welding of those materials, where in some cases a pneumatic welder wouldn't even, you literally can't weld that material. You pour a bunch of heat into that plastic part, and by the time you open, remove the heated tool, and bring them back together, there's a skin on the top of the surface, and you've got a cold weld. It's going to leak. It's going to fall apart. Servo, when we come together to weld, here's another critical portion where you need to apply a bunch of force into the plastic parts. So look at the pneumatic side. How much force is going into the weld joint? We don't know, because some of the force is going into the plastic part, and some of it is going into the stops, and it can vary part to part. You might have great parts for a while, and then something slightly changes, and now a bunch of that force is going into the hard stops, and not as much as going into the part. And it could lead to leaks or poor strength. With a servo welder, there aren't any hard stops, so all of the forces that we're applying, which we can measure, are all going into that plastic part. There's nowhere else for that force to go. Was there a question that came in? What's the cycle time range for the welds?
Yeah, what material and then general part size, just general dimensions do you have?
Yeah,
for that one, Owen. We'll show you the next slide here. We've got to show the open time.
Yeah,
that Jason's talking about, the speed. So if you recall, one of the issues we talked about up top was materials that are difficult to work with because they skin over so rapidly. Now this video is not sped up at all.
They're not going to believe you.
They're not going to believe me. It's going to blow their minds.
Loading 2 parts here. Okay.
And this one, does this do the part pickup as well?
Yep.
You can start part pickup.
Yeah.
Whoa.
It's shocking. Yeah. I know. Oh, right?
So fast.
Did you see how quick that open time was? I believe the open time, we can go back in time. I'm pretty sure it was 0.8 seconds.
Let's watch again. Mm-hmm. So again, the part pickup, these parts are coming, the top is already on there.
Yeah, the little black component.
The parts into the nest when that top one comes into contact. That's
melting.
I'll get your stopwatch out there, Owen.
So this application, I don't know, what is this, 10 seconds? It might be less than 10 seconds for the total amount of weld. Mm-hmm. That is a pretty quick hot plate welding time. Sometimes, we're closer to 20 seconds total weld time. There are some applications, I think very large parts, that are limited. You're only allowed to use lower temperatures. Mm-hmm. When you're welding at 450 degrees Fahrenheit, and you've got a lot of surface area that you're trying to melt, that can increase cycle time a lot. So we've seen 40 seconds of total weld time be possible. Yes. Thank you, Rob.
Yeah. Throwback to the past.
Owen says the part is a circular cap, 3.5-inch diameter. Weld joint is about 0.05 inches, so about 50,000. Okay, so that would be a fairly quick weld time, although the material too makes an impact. If it's something polypropylene, we can melt that pretty quickly.
Probably pretty comparable to the cycle you saw there. Maybe at 1 second heat time, 1 second seal time.
Sure. Yeah, but it's all, it's general range until we're actually able to test it and see how does the part perform at that rate, and is it getting you the strength you need? And if not, we might have to make some adjustments which could affect the cycle time.
Yeah, exactly.
What type of heaters are used on the weld plate? How easy are they to replace when they fail? They are, so in most of our welders have a cartridge heater that is inserted from the back of the tool. So you can't really see it in this image here. There's the center there. Actually, can you point out that centerpiece?
This is a sheet metal sheet metal that's blocking it. But you have all these cartridge heaters.
Yeah, that are going front or going back to front as you're looking at this. Yeah. And they're spaced a couple of inches apart. And there's, I don't know what the number is, a lot of them in there. And then there's also thermocouples inside of that platen as well. So that what we typically do is we heat what we call the carriage. Mm-hmm. So that's that main plate that stays with the weld. It's part of the capital. And then the tooling is bolted on top of that, and then we allow conduction to bring the heat to the heated tools.
Yeah, this is the tooling. So there's not any heaters in there, but you can conduct the heat up to the parts. Yeah.
Now there's a configuration of our Titan welders, and then of course we make custom machines too. So custom hot plate welders. There's plenty of times where we actually don't put any heaters in the carriage. We put them into the tooling. So an example of that, I'm going to grab control from Mitch here a second, is back when we were looking at that Teflon tools. So this on the right here, this is the tool, and there's actually heaters inside of that tool, and then we actually have heat isolators that are making sure that the carriage itself remains as cool as possible. So it depends on the situation whether we want to put the heaters in the tooling or whether we want to put them in the platen, but we can do either. And we try to make them as easy as possible to replace, because heaters do occasionally burn out. But I've personally never done it before, so I don't really know how hard it is to do.
Yeah. I mean, it shouldn't be it should be a pretty quick maintenance. Yeah, I mean, it should be like a full day downtime here. That should be maybe a few hours. Two great questions. There's what common polymers are suitable for this kind of welding? Do you want to pull up that slide? Yep.
Okay, so here's some really good examples that are hot plate weld compatible: polypropylene, ABS, polycarb, acetal, PMMA. Like you can kind of see all these different examples over here. There's a couple that you want to steer clear of, and that would be nylon and PBT. Mm-hmm. Those are very they're really sticky. And so it's really difficult to get those to not stick. Even with non-stick coatings, it's hard to get them not to stick like crazy to the heated tooling.
The challenge too is they require higher temperature, higher than what your Teflon coating will allow. So you can't, there's not common coatings that are common to the market to prevent those from sticking. So you typically use non-contact welding methods, vibration, IR, hot plate hover for those sort of technologies.
Mm-hmm. Max says, why does the welding surface amount affect the cycle time when all the surfaces contacting the heat plate at the same time?
That's great. The way you're phrasing the question wouldn't be an issue. But typically with the larger parts, there is an amount of warp that you have to take out of the part and plane even. Yep. So if your parts are coming in perfect every time, then you'd probably have the same cycle time as the smaller parts. Yep. But typically there's an amount of time that's needed to plane the surfaces even and then heat the weld rib up.
specifically on degas bottles and probably in other applications, the welder is very thick. Mm-hmm. And there's usually, because of the way plastic shrinks after it's molded, mm-hmm. there is sink in that weld mm-hmm. surface, and on a big part with lots of internal ribs. There's sometimes pretty large amounts of sink to the point where we have to melt a lot of depth, like a 100,000th of an inch, so like 0.1 inches into that plastic, which doesn't sound like a lot, but it is a lot, especially on a large surface area. You get a lot of force, and you're pushing to get full weld penetration. So,
yeah, glass fiber content. Typically we want to stay below 30% for tool wear. You can run those sort of higher glass contents, but expect to recoat your tools more frequently. Yep. If you're to do that.
High temperature polymers. So polyamide is not on PA. That's one of the ones that we want to steer clear of. PEEK. Great question. I personally have not seen PEEK be hot plate welded. We have limited experience with the welding PEEK in hot plate. We've tried to process PEEK a lot of different times. Very high temperature. To be determined. I don't know if anybody on the call maybe has experience trying to do hot plate welding with PEEK, and you want to chime in. But as far as I know, I don't know that anything about PEEK makes it totally unweldable. It's just a very high temperature, so it would be a challenge.
Yeah, and kind of a sharp glass transition zone too. It's a challenging material for a lot of different welding applications.
Isaac asked, can you do concentric welds or welds inside of the perimeter? Yes. Mm-hmm. How would you check the efficacy of the internal welds? You couldn't necessarily visualize. It's usually destructive. So, if it's a hermetic seal, then yes, you can do a pressure test and find out. But even there, if all of these chambers are interconnected, like a degas bottle, they're usually all connected to each other. One internal leak test isn't going to tell you whether there is a leak between mm-hmm. the weld surface. So a lot of cases, it's a destructive test where you're cutting your part up into a bunch of little sections so that you can run tensile tests on some of those internal welds. Once you've dialed your process in, it's expected that those welds would stay good, and then we're looking at other parameters in the welder to detect whether there's a part issue or something.
What about COC? We welded COC with Teflon sheets. COP, I don't actually know COP.
Yeah, I don't know that one either.
And then PS, I'm not sure about.
But we can look into that, Brian, and follow up with you. Is it possible to weld similar, like PC with PC ABS? Yes.
Yeah. Just as long as you have compatible materials.
Yeah.
Because the way that you'd vary that is you can touch off on the hot plate on the top if a certain material requires more melt time than the other. So you just hold longer on one portion of the plate and then bring the other one into contact so that you'd have a shorter melt time for the second part.
Max says that PEEK has a very rapid cooling, so his machine wasn't fast enough. I'm curious, Max, do you happen to know what the open time was? I'm curious. What I want to know is, can our new Titan hot plate welder be fast enough? It's wicked fast. It'll blow your mind.
Mm-hmm. Yeah. I'm gonna, just because we're running up on time here, I'm gonna bring this to a close here. We are gonna hang on until 12. The webinar is meant to go till 11:45 here. We'll hang on until 12 to answer any questions as they come up, though. So again, this is the starting of the presentation. We talked about the common issues with plastic welding, and that's plastic welding in general for all different technologies. That's where our Titan series welder and Extol's hot plate welding helps solve a lot of those problems. So it is the fastest welder on the market. It has the highest force capacity of any welder on the market as well. Very precise dimension control, helps solve those warp issues, as that proprietary non-stick coating, and then has the higher temperature. We typically run in the, again, 800 plus. A lot of welders can only run at 750 max. Mm-hmm. So it helps us allow a lot of different areas. Extol 2, with hot plate welding, we can configure that solution to really any format, whether it's the small modular or whether it's the larger pallet welding one. We've got some pre-engineered solutions. Quick history of Extol. Hey, great segue again. These people in the crowd, they
like they know it's coming.
They must have seen this presentation or something. So 40 plus years of plastic welding experience. We're an integrator focused on plastic assembly. I'll dive in a little bit more what that means. So our tagline is we solve plastic or complex plastic manufacturing challenges. You can see we've got the X here. This X represents kind of the two portions of our business, the plastic welding expertise that we have and the custom automation expertise. The plastic welding expertise allows us to approach those very tough plastic welding challenges.
Like welding peak.
Like welding peak, sure. Yeah. And then we tailor that equipment, like you saw with the multiple hot plate formats, to your specific needs. So with Extol, you don't compromise. You get a configurable plastic welding solution that's optimized for your performance. We have standard products, but we want to tailor those to whatever that is, and we'll help handle surrounding automation. So that's a bit about Extol too. If you have any or need any help with future plastic assembly projects, we got the QR code. I know there's IT stuff. Maybe you don't want to scan the QR code. You'll have my contact.
Click it. This is a clickable link, so you can actually click that right now if you want to.
Our website.
Take all the viruses.
Right. Then we'll get all your information.
Yeah.
It's the plan. That's what it's all is. It's one big ruse just to steal all the. Our website, we have a support area where you can submit your projects there. We can help reach out, discuss those projects. Mm-hmm. You've got my information as well, Jason's information. Continue to reach out. Again, my role here, I help customers find what that optimal joining technology is for the application, and then tailor that solution from a manufacturing perspective, whatever they need.
Yep. A couple of questions that are coming in, and thanks, Scott. First of all, Max said we need to close within 3 seconds. That sounds easy with a Titan.
Well, depending on the size of the part.
Yeah, depending on the size. But I mean, the open time of that one example was shorter than 1 second, and that was not a Titan. So the Titan is faster than that even. Somebody, I'm sorry, I can't pronounce your name. Considering the need to prevent water leaks, yes, these are hermetically sealed parts. What's the ideal surface design for welding? So we have hot plate welding design guidelines on our website, and you're welcome to access that. I can also include that in the follow-up email that will go to all the attendees afterwards.
Yeah, that'd be really great, actually, if we could include that brochure for them.
Yep. And again, take advantage of our process development center. Basically, all you need to do is reply to the follow-up message or your registration confirmation or any email that you've ever gotten from somebody at Extol and say, hey, I've got a welding project that I'd like some help with. And whoever that person is that you're emailing will get you to the right place. And we'll basically, it's simple. If you want somebody to look at your weld design, you share your CAD with us. We review it with a lab. They can put together a report and say, hey, here's some areas where you can make some improvements that'll make your part weldable. Here's some areas where you everything's fine, and we can kind of work through that with you. Yeah. Tom
asked, why, when would one prefer hot plate welding over other welding processes like ultrasonic vibration? Is it usually cheaper? There's a couple different reasons. I think I'll probably just speak to ultrasonic first and then speak to vibration after. Typically with ultrasonic, there's a kind of size requirement that you're dealing with. Once you get past a certain size, to get the energy into energy director without blowing out in other areas of the parts gets pretty challenging, especially with some like polypropylene, that directing the energy becomes a bit challenging with those larger parts. And then for vibration and ultrasonic, they both have flash that flakes off in the form of particulate. So if you have a particulate requirement that you need to stay under, that's where you typically use hot plate welding. The other piece of that is kind of some A-surface marking. Both of those tools have the potential to mar the A-surface when you're welding. Vibration has vibration welding. You've got specific tooling details that are required, and you can see oftentimes the knurling from the vibration tooling on a specific part. Hot plate welding, you wouldn't have that as well.
What's the weld failure rate? It's very dependent on the customer's parts, but a well-optimized process and well controlled. I mean, within reason. We're not expecting that all of the parts coming into a plastic welder are perfect. We know they're not. They're plastic. And as we mentioned in a webinar not too long ago, plastic be plasticking, and it warps like crazy, and there's lots of inconsistencies. But it's reasonable to expect a scrap rate of 1% or less.
Mm-hmm. Yeah.
If it's higher than that, there's issues, and we should fix those because they shouldn't have to be that high.
Yeah. And typically, I'd say those issues not very typical from the welding process itself. More of those that the incoming parts fall outside the typical process window. Mm-hmm. So if you've got parts that are consistent over and over and over again, you're going to get consistent welds over and over and over again.
Mm-hmm. Did we answer all the questions?
We've answered every question, every possible question about hot plate welding that could ever be asked.
Mm-hmm.
Has been answered.
Oh, there's one here that says EVA foam. One supplier said 140 to 180 C hot plate weld temperature. But curious to hear how a foam process compared to thermoplastics. Well, as long as the foam would need to be a thermoplastic as well. It can't be a thermoset because it would not melt.
Yeah.
I don't know about EVA foam, like what is that made of? But I also, with a lot of air inside of it, I would guess that the collapse on a foam like that is going to be crazy. I don't have any experience trying to weld foam to a thermoplastic.
Yeah, I don't know how stiff that is.
Yeah.
How stiff the EVA foam is. There's a lot of other technologies typically used for foam. I'd say joining them together, ultrasonic, some staking technologies, film sealing.
Mm-hmm. Last question for the audience, if people want to chime in. What topic would you like to hear about next? I have a whole schedule of webinars lined up that we plan to bring to you, but I'm curious if you guys have certain topics that you'd really love to hear about. Let us know. Whatever, we want to make sure that the discussions that we're having with you are relevant and meaningful. Mm-hmm. Laser, spin. Cool. Laser. Ooh, 2 for laser. Okay, let's get laser. We're going to tally started. Yeah, we'll look at this laser. Okay, well, we're going to definitely have to do a laser one. I'll write this down.
Yeah.
I do plan on doing a laser one, but maybe I'll have to schedule it for a little bit sooner rather than later. Mm-hmm. Do we handle threaded insertion? Why, yes, we do. Mm-hmm. There's a couple different ways to do that, but we'd love to hear about what you're looking for. Laser. Okay, lots of lasers. Max, you might have to wait on the spin welding. You're the only spin welding vote so far.
Yeah, we do have resources, Max. If you got any specific questions about spin welding too, again, reach out. We can help answer a lot of those questions. We've got some design guidelines on our website. We got some webinars, some pre-recorded webinars that we've done on spin welding.
Yep. I
will say we even updated since the spin welding webinars, where there's probably information that we have in there now that we should share that's more up to date.
Yeah. And last plug is we can come to you. Mm-hmm. We can either do a webinar with just you and your team. That usually allows for a little more open conversation because you don't have to worry about competitors hearing the advice or hearing more about what your project is. But we really like to come on site in person to your facility and do trainings with your team. So that's a great way to get exactly a tailored experience. If you want to learn about spin welding and threaded insertion, and those are the only 2 topics you care about, great. We'll come to your facility. We will do the training with your team, look at whatever project you're working on, and give you advice and recommendations. And we can talk about what makes sense to help move your project forward.
Yeah. And then they said too, you are also welcome to come to Extol. And second that.
We've got lots of parking.
You can come to our applications lab. That's a great place where you can see all the different technologies. Mm-hmm. And you even have an opportunity to use some of the equipment if you have a specific application.
You can all see the expanded building. We expanded. Yeah. If you haven't been here in a little while, or you've never been here, the building is larger than it used to be.
Yeah. Just imagine a warehouse space, but bigger.
Yeah. We are in Zeeland, Michigan, and that is, for those of you who don't know Michigan very well, it's on the west side of Michigan.
Do the hand thing, Jason.
Okay. I always do it backwards. Let's see.
No, that thing.
Is this mirrored for you? This is
The other way.
This is the thumb. Am I doing it right?
Do the other way.
Okay,
Yeah.
this side.
There it
This is where Detroit is. This is where Zealand is.
There we are.
So it's nice and close to Lake Michigan. If you've never seen Lake Michigan before, you can come see it.
Yeah, and this time of year, you might be lucky enough to get some lake effect snow. So if you're into that, I'd say come.
Yep. All right. Thanks, everybody. We appreciate your time and all your questions. If you have other questions, please hit us up via email or give us a call. Thanks again for joining us, and have a great rest of your day.
Yeah, thanks, everyone.